Well, it's really good to be here this morning. I always enjoy coming down to Logan. That's a beautiful place, and I find the agriculture down here fascinating too. Just enough different than up in the Magic Valley of southern Idaho to make it more interesting. The information that I'll be talking about today in terms of actual field data were all collected from over in the Barley Rupert area in the Snake River Plain. And so for those of you that may know that area, to the extent that things apply from there to here, you can judge accordingly. But I think a lot of the concepts I'm going to talk about are going to be the same no matter where we are. I wanted to spend just a short period of time talking about soil water holding capacity, because later on I'm going to tell you, well, you can shut the water off at soft dough if you have a couple inches of stored water in your soil that you can actually use by the plants. Well, that causes a question to be asked. So how do I know how much water gets stored in my soil? We have this kind of a general relationship that looks at soil water content and also at water holding capacity as you change from sandy soil textures to the heavier clay textures. What we're looking at in terms of a grain crop, let's look at a sandy loam soil. Say, well, for a typical sandy loam soil, the water that's held between permanent wilting point and field capacity is what we call available water. And gosh, I sure wish people hadn't called it available water 100 years ago. Hindsight's wonderful, because typically we can only use half of that available water before we start seeing a yield or quality penalty. And so some of us talk about readily available water being kind of the top half of that water tank, if you will. They chose permanent wilting point and field capacity, I guess, because they were somewhat observable. Field capacity is kind of the water content that you have in the soil a couple days after irrigation. You irrigate, things are pretty wet, the easily drainable water moves on out, and what's left can be held for a long period of time. Well, you can kind of see that. And then on the other end of the spectrum here is a place we never really want to go, and that's called permanent wilting point. And it's just what it sounds like. The soil gets so dry that that plant wilts, and it's so dry that when you add water back, it's not going to recover. We generally try to stay away from there. And so for many crops, grain included, most of the season we would say we can use half of the water that's held between these two, between field capacity and wilting point. We can use half of that water before we start seeing a penalty. And I'll talk a little bit more about that later, because at the very end of the season, the plant's a bit more forgiving and we can use a little bit more water. Now, translating that curve into something that may mean a little bit more to you, we have the average water holding capacity of various soil textures here, and these are certainly averages in terms of inches of water held per foot of soil depth. So for a very sandy soil, we would say that the water holding capacity, or the available water, is 1 inch of water per foot of soil depth. The more common soil textures, at least in our area, and I suspect down here, are going to fall somewhat in this range. The loams, the sandy loams, the silt loams, and maybe even the silty clay loams or whatever. Notice that with a loamy soil, we have and I classify the sandy loams in here as well, about 1.7 inches of water that can be held between wilting point and field capacity for every foot depth of soil. As you move into the silt loam soils, up around Rexburg in a really light silt loam soil, you're probably about 2 to 2.1. You get down into the Magic Valley, Twin Falls, Rupert country, and you're up 2.4, 2.5. It all depends on what size those particles in the silt range really are. If you got a lot of big silts, you're probably at 2.1. If you've got a lot of fine silts, borderline clay, you're probably up 2.4, 2.5. What are the typical textures that you all are working with? How many have a fair number of fields that have a sandy loam texture? Not many. Silt loam, clay loam. kind of gravelly alluvial soils. So you see a wide range. And what I typically do is I'll go to the NRCS soil survey. That has really nice water holding capacity information for your specific soil on that specific field. Great resource to go to flesh out these general recommendations for your specific site. Because this becomes the basis when you can shut off the water at the end of the season. You really need to know what you're working with. When I put this slide in, I put it in just for this line, but I got to thinking as I was sitting back there, this is kind of important too. This talks about the depth of wetting if you added 1 inch of net water application and you had uniform soil moisture with depth, which is kind of tough to find. That's more of a theoretical thing than reality, but it still gives you a pretty good idea. How many of you are irrigating with center pivots? How many with hand line, wheel line, solid set? How many surface irrigators? Okay, full range. With center pivots, we would typically run the pivots so that in mid-season, maybe you're doing what, a lap every 2.5, 3 days or so, somewhere in there I would guess. If that's the case, you're typically coming back and the soil right ahead of your pivot is somewhere in this moisture range. 35, 40% of that available water that's been depleted. So basically, center pivots look at this line. If you're working with surface irrigation or set systems, you're going to be looking more at this line. You can use about half of that available water, or water holding capacity if you want to look at it that way, before you irrigate again, because with these systems you can always add enough water to refill the soil. With a center pivot system, at least up our way, you're pretty well limited on how much water you can add without getting excess runoff and getting the whole thing planted. Typically, we have the difference in the amount of water we can add, and it also means we'll see a little later how we operate a center pivot relative to the others. But let's look at the silt loam soil, and if you're using a set system and you're down 50, you've used 50% of your available water, you put an inch of water down, that may wet up 10, 12 inches deep. It's found enough places for water to be stored in that soil, it's only going down about 10 inches or 12 inches. Now, if you were on a really sandy soil and did the same thing, that same inch of water is going to go down about 2 feet. It's another way of expressing water holding capacity. A sandy soil just doesn't hold as much water per foot, so that 1 inch goes a whole lot deeper. This, I think, could play in toward the end of the season when you say, well, I can look by the numbers and say I need 2 inches of usable water, and that means for my soil that I need to wet up 2 feet deep. How do you know you wet 2 feet deep with an irrigation? You know from experience. The thing I forgot to throw in the car this morning when I came was a tool that I use. It's just basically a hunk of 5/16 steel rod with a little bit bigger ball bearing welded on the lower end and a T-handle across the top. And you can push that thing down in a moist soil, and it goes down easily in a moist soil, assuming you don't hit big rocks, until it hits the dry layer. And so I use it a lot for pastures. You can go out in a pasture and you can poke around with this thing and you can find out very quickly how deep your moist water is. So typically you can go out, you can water, and then start probing around and say, okay, I went down 15 inches. That lets me think about this, and if I'm wanting to refill the top 2 feet, maybe I need to add a little bit more water next time. It's a way of kind of getting some feedback on how you're watering. You do the same thing with grain, and as I'll show you a little later, grain typically will extract water from down to about 30 inches to 3 feet if it needs to. If you have the luxury of that much soil, that's great. We have folks out by Castle Ford that are just smiling if they have a foot. And hopefully you're in better situations than that. You can also use different indices of how wet your soil is. This is some information I developed a number of years ago for folks that use tensiometers or watermark sensors. And the nice thing about watermarks particularly is you can bury them out at 2 or 3 feet, and you don't have to take a bucket auger or whatever to check the moisture down there. You just kind of look at what that sensor's reading. And so those kind of things will relate whatever the reading is to the amount of available water you have at that time. So, for example, if we said we wanted to irrigate when the available soil water was 50% and we were in a heavier textured silt loam, we would come down to here and we'd say we'd better be irrigating by the time that meter reads 75. Because when it gets to a larger number than 75, we're beginning to stress the crop. You know, that kind of information is available. There are many sensors out there, many data loggers. Most of them work pretty well. They all require some degree of on-site calibration by the user, if you will, to figure out what this number really means for me on my soil. You know, none of them can come straight out of the box and be usable without a little bit of trial and error and local experience. But these kind of things are very useful if you want to be able to check on the status of a field and you're sending someone out that started working for you yesterday and they don't have the experience that you have of taking a shovel out and feeling the soil and saying, yeah, I know what's going on. They don't have that experience. So these kind of devices are much more useful in transferring that information to somebody with no experience. One of the other things that's useful for knowing how you manage water is knowing how much you're putting on at one time. For those of you with pivots, you have a pivot chart, hopefully there in your control panel somewhere. That gives the relationship between, they can call it different things, the percent speed, percent something, which is really the percent of the time that outer tower is operating. 100% means that outer tower is running continuously. 50% means it's on half the time. Your pivot chart gives the relationship between that percent on and how much water you're putting down. And so that's a really important thing to have for your particular pivot package. One of the things that dealers use in kind of, dealer speak, I guess, is they talk about pivot capacity in terms of gallons per minute per acre, which isn't usually what the rest of us talk in, but that's how they size and design pivots. In our area, maybe 6.5 to 7 gallon a minute per acre would be the range. That would mean we have enough water to handle most of our crops. And so what you can do, if you know that number, is to be able to calculate what your application rate in inches per day is. You'd really like to know that to know if you can meet mid-season demand or not. So in this particular case, we would say center pivot or linear move application rate, the gross rate, which says if I take the gallons of water and spread them uniformly across the field, the gross rate is how many inches per day that I'm actually pumping. Now, not all that gets into the soil. Some gets lost to evaporation, wind drift, and other losses. So our net application rate takes that gross rate and uses only a part of it. Usually for a low pressure pivot, it's about 85%. So the main equation here says gross application is gallons per minute per acre times 0.05303. So in this example, we say what's the gross and net water application rate if you have a 125 acre pivot with 875 gallons per minute water supply. The application efficiency, we would say, is 85%. So gallons per minute per acre is 875 divided by 125, 7 gallon a minute per acre. The gross application is 7 times this magic number, or 37 hundredths of an inch per day. But we can't use all of that. Our net application then is 37 hundredths of an inch per day times 85% divided by 100, or 0.85. 37 hundredths of an inch times 0.85 gives you 32 hundredths of an inch per day that you could actually count on using from that center pivot. And at least in our area, that will meet the vast majority of those hot days for wheat growing, and I suspect you're just enough higher in this area that might do really well for you as well, I would guess. So that's how you would figure out, if you didn't know, how much water a particular pivot can put on in terms of inches per day. Now with set systems, usually the best way to do that's from a table or a slide rule or something that takes into account nozzle diameter, spacing along the line, riser spacing on the main line, and when you crank in all those numbers, I could have put an equation up here. You know, engineers love equations, but you don't generally, so I didn't put them up. Generally, we can get that with from a slide rule or a table or something. And then don't forget to consider the fact that for these systems, only about 65 to 70% of the water you pump is going to get where you want it. And so your net application is gross times 0.65 on really windy, hot days, or a poor quality system needs some maintenance. About 0.7 if you've got a nice new system and relatively moderate wind. Well, day-night application isn't really much of an issue here. I show a series of slides here to talk about some of the variability. This is alfalfa information that came from Agromet, and what it shows is the long-term average, and then the green dots are from particular years. And here you can see you have a wide variety. Now 2006 and 2007 were memorable years up our way. Look at how many days were well above the average. Now when you're growing grain, you know, this is alfalfa peak, and so you're looking at what's happening you know, here July, August. What time is soft dough going to hit around here? When would you expect the crop to be at soft dough? You know, it's going to vary depending on where you are, of course. Let's say mid-July. And so if you come in here mid-July, we're up about in here, right about the peak. And you can see that in 2004 we had a few days above. 2008 we had quite a few. 2007 we had quite a few. 2009 not so much. We have a wide variety in how many really hot days we can have during that period. You see a lot of variability from year to year. And so we need to have a little bit of a slop factor built into our recommendations. So when you look at small grains, you say, well, what happens if you stress small grains in various crop stages? If it's in the vegetative stage, except for tillering, it typically tends to shorten the plant. I did 3 years worth of early season water stress up in the north of Rupert area. You know, those folks ought to fund me to do those studies every year because it brought rain. I mean, I only had 1 year that had reasonably good numbers. It rained at the wrong time every other year and kind of washed me out. You know, that happens. But what it did was I could show that by stressing early, I could shorten the crop by about 6 or 8 inches with very little yield or quality reduction. Now, I will be the first to kind of yell and scream, please don't do that as a management practice, but that's what happens. I don't have enough confidence to do that myself, to stress it early, because if you do stress during tillering, you're going to permanently lose yield potential. Tillering, you know, you're sending up additional tillers. You stress at that point, you're going to end up with fewer tillers, fewer potential heads, and any reduction in yield you take there from stressing that crop during tillering, you can't reclaim. You can only hold on to what you've got left. And so be very careful, particularly in some of your lighter, low water holding soils. Those can kind of dry up on you early in the season, you know, when you're just coming out of the winter, and you can end up with those things pretty dry before you know it, and possibly stress it during tillering. So particularly watch on your low water holding soils that you don't. Now, the crop's not real big at this point. You know, it's maybe 6 inches tall or so. It's really not very big, and so it's a little deceptive. And I find it remarkable that you start limiting your crop yield when you do something to a crop that's that little. But that's what happens. Tillering, you limit the number of heads, and you limit the size of the head as well. So vegetative, you don't do much in terms of yield reduction if you have a 10% shortage in water application from what would be acceptable. If you have that same 10% deficit in irrigation relative to ET during flowering, you're going to limit it by 6.5–7%. Yield formation, you're going to get incomplete head fill, kernel size, you're going to limit at about 5.5% of your potential value for each 10% ET deficit. Barley, we can look at this a little bit differently. 10% ET, well, what does that really mean? So let's say if we have a 1-inch deficit in each crop stage, what does it do to us? A 1-inch deficit in vegetative is about 2% of the maximum yield. Tillering, we talked about that. Boot to flowering, 1-inch deficit is going to cost you about 11% of maximum yield. Flowering is going to cost you about 16% of the maximum yield. Not a good time to be stressing. If you are an inch behind at soft dough, and then you continue with reasonable irrigation after that, you have about a 9% yield hit. After soft dough, we say there's very little yield reduction if you have at least 2 inches of usable water in the root zone, and we'll talk more about that. This is sort of the number that we come up with, 2 inches of usable water in the crop root zone. If you took a 1-inch deficit and spread it uniformly across the entire season, you get about a 6% reduction in yield. Spring wheat, the same thing, 1-inch deficit, 2%, wheat to flour about 16, flowering just about the same thing. And not that different for winter wheat as well. They all respond fairly well. Now this was from a number of years worth of work, 65 to 78 at Kimberly. Dr. Jim Wright did this, and after a while, when you're stuck trying to make a copy of a copy of a copy of a copy, the clarity gets a little questionable here, but I've tried to go back and find the original data, and that doesn't seem to be really readily available. So this is the best I can do. But what I wanted to show you is look at the variability year to year on what that water use is during the peak part of the season. That's why the best irrigation scheduling technique is your shadow out there in the field during this time, checking it out. What are you seeing? How's that crop doing? The other thing I want to show you is you have the rise, you have the peak use time, but look how fast this falls off once you get past that peak. Grains are really deceptive. They hit a point and they shut off on water use, and I think we're all of the mentality that we've been trying to add all the water we could to meet that peak use part of the season. All of a sudden the plant shuts down and we're not necessarily seeing that, and so we keep pouring the water to it. And that's when we can put on extra water and hurt ourselves a little bit. So this is the time when it really pays to be vigilant and be out there watching what that crop is doing. Again, some other 30-year average ET for Kimberly, and again you see how fast that falls off. Well, basically we want to make sure that we have adequate early season water, and we're going to spend the remainder of the time talking more about late season, which is right here. Here we have 4 years worth of data from spring wheat. That'd be 3 years from, it'd be 4 years from north of Rupert, and in 2000 we also had some information from Rexburg as well. And so what you see here is relative grain yield. This would be the yield at this treatment divided by the maximum yield for the treatments. We had our highest yield when we cut the water off with a reasonably full profile at late soft dough, right there. When we cut the water off at early milk, we had about a 70% of our maximum yield. We waited until late milk, we got up to maybe about 78% of maximum yield. We ended up at early soft dough, we ended up maybe 90%. At soft dough, we have a lot more scatter, somewhere between 90 and 100% of maximum yield. Late soft dough, when we're well into that soft dough stage, we had the best results. And then after soft dough, it either stayed the same or it dropped. 2000 was a year where we had a lot of blacktip. The conditions were right for blacktip. Yield dropped off, and quality certainly dropped off, and I'll show you some of that in a minute as well. What you can see here is it depends on how important your water is and what the price of grain is. If you have a high value crop that you need to be watering at the same time as spring wheat, if wheat prices are down, you could look at this and say, gosh, if I cut off water at early soft dough, I'm still going to get 90% of my maximum yield, and I can switch that water over to this other crop where I'm going to make more money, you know, if that's the case in this particular year. What I work with is we have some high lift pumpers, and they begin to look at this and say, you know, that'll save me a couple of irrigations late in the season, and those are very pricey irrigations when I'm lifting several hundred feet. So heck, if I can avoid 2 irrigations and still get 90% of the yield, it makes sense to me. So this is the kind of response curve that we can look at for a number of decisions. Here we have it for winter wheat, and this year in 2001 we got a little bit carried away and decided to cut some off at flag leaf. We still got about 70% of our maximum yield, but that was from a soil that had good water holding, and it had enough water to actually get it through to a reasonable yield. This at milk, you know, we had about 85% or so, which is surprisingly high. Pre-soft dough, you know, up close to about 92 or so. Soft dough was maximum. Post-soft dough dropped off in all the years that we had tested. Then we go to malting barley. This was done at Barley at the Coors station there. We cut off at milk. We had a little over 80% of our maximum yield. Early soft dough, we about 90%. Soft dough, 100. And post-soft dough again dropped off. You're beginning to see a pattern here. When we say we cut off after we had filled the top 2 feet to pretty nearly field capacity. That was kind of our way of doing it. So we had good moisture in the top 2 feet, and then we cut off at that crop stage. And so you begin to see a pattern. It's low, and it increases to a peak somewhere around soft dough to maybe a little bit after. And then when you get, you know, a week or so past soft dough, getting close to hard dough, in a number of cases, we see the yield decline. And so what does that tell you? Well, I've spent the time, effort, money, and water to put on maybe 1 or 2 more irrigations, and I don't have any more to show for it. And in many cases, I have less to show for it, either in terms of total yield, in terms of protein content, test weight, or reduced crop quality because of blacktip. So in general, our maximum yields occurred when we had a reasonable amount, probably 2 inches of available water in that soil, in the root zone, and cut water off somewhere around soft dough. Seems to be a pretty good pattern for wheat and barley. This again shows some information on quality for barley over that 3-year period. We had the plumpness didn't really change anything statistically. Going from milk clear to post-soft dough. We had the color, and it actually dropped off a little bit with the late watering. We had the protein content, and it drops off a little bit as you add additional water. And so, depending on what's important to you, you can see how different factors behave on the quality side of things as well. Now, this was in 2000. We did have it was a bad blacktip year. On the plots where we shut off the water at milk, we had 3% of the kernels infected by blacktip. At soft dough, we had 4%. And when we watered after soft dough, this is again with sprinkler irrigation, we had 9%. Now, the barley contract allowed for at least no more than 5% of damaged kernels. And so these first 2 made grade, this one didn't. That was in a really bad blacktip year. And we saw that at Rupert, we saw that at Rexburg, we saw that everywhere that year. How much water does a grain crop use in different crop stages? And again, these are averages, but it gives you some feel for how the water use is distributed. Here's a 2-row malting barley, and here's a hard red spring wheat. Not a whole lot of choices, but these we have good numbers on. Emergence to milk took 11 inches and 14 inches. Milk to soft dough, about 3.5 inches. On the malting barley, it only took 2 inches over here. Soft dough to hard dough, about 1.9 on the malting barley, 0.8 here. Hard dough to harvest, 0.8, 1.2. This is kind of where we come up with that general rule of about 2 inches of water, of good available water held in your root zone. You know, this is about 2.7, so a little high, and this is right at 2. Somewhere right in that 2.5 inches of good usable water in your root zone is where we ought to be to get from milk or from soft dough to harvest without any yield or quality reduction. And again, these are averages. The seasonal total, about 18 inches, about 18 inches. So this is kind of where that water use occurs. So what this means then is we want to have at least 2 inches of available water at soft dough. This is going to depend, as I'm going to show in the next couple of slides, on how deep a root zone you've got and what kind of a soil you've got. But in general, if you've got a full profile, at least 2 feet deep, at soft dough on a deep, non-sandy soil, you know, silt loam or heavier, you can stop irrigation. If you're on a shallow soil or a really sandy soil, you're going to need about 1 more irrigation after soft dough. One of the tools that I really value is the USDA NRCS Estimating Soil by Feel and Appearance little folding handout. It's a really nice tool that lets you do a pretty low-cost way of evaluating how much water you have left in the profile. In that little booklet, it has a series of pictures like this for several different soil textural classes. You know, sandy loam, silt loam, heavier clay loams. And for this, in this picture, for example, they all follow the same pattern. They say go to the field, go to the depth that you want, take some soil, get a bucket auger, shovel, post hole digger, whatever, get the soil, squeeze it in your hand, and then look at it and feel it. If it looks like this, you know, just a few crumbs sticking here, and it has this kind of a response. In this case, it's slightly moist, it forms a weak ball, very few aggregates break away, very few aggregates breaking away, no water stains on your hand, clods flatten with applied pressure, and on this particular texture, we're somewhere in the 25 to 50% available, or we're this much depleted. And they have the whole methodology there for determining how much water you have remaining to work with. What I tried to do is to break this down a little bit more for what I would consider usable water on a sandy loam and a silt loam soil. Sandy loam, 1.7 inches per foot available. We can use half of it, so we can count on using 85/100ths of an inch per foot. If we have a 1 foot root zone, that gives us 85/100ths of an inch of water the plant can use. If we have a 2 foot root zone and we're at field capacity right after we irrigate, it has 1.7 inches that plant can use. If we have a 3 foot root zone, it's got about 2.6. You move down, and we said we ought to have at least 2. Silt loam, 2.4 inches per foot. We can use half of it. That gives us 1.2 inches that we can use out of every foot of soil. So there's 1.2 inches. 2 feet, we can use 2.4 inches. 3 feet, 3.6. Well, you stand back and look at this and say, well, you know, I could probably, if I irrigated and filled the profile up and I had 2 feet to work with on a sandy loam soil, I could probably squeak by with 2 feet if I shut off at soft dough. If I'm on a little heavier textured soil here, yeah, I can shut off at soft dough. If I just irrigated and that 2 feet is filled to field capacity, I can shut off with pretty good confidence. And so you see the effect that different soil texture has to say. Just in summary here, watering past soft dough did not seem to improve the yield. Statistically, it never did. It may reduce test weight and protein, may increase blacktip infestation. It uses water and energy for no additional benefit, and it can leach out crop nutrients that are moved down deeper and maybe not available for the next crop then. So what in the world is soft dough? Well, everybody has their own definition of this. Some people say, well, gee, squeeze the kernel, inside of that kernel is somewhere between milk and hard dough. I was giving this presentation in one place, and one of my beloved county faculty said, yeah, it's the zit factor. You squeeze it, if it looks like what comes out of a zit, it's probably about soft dough. I hadn't thought of it that way. But, you know, Basically, it's not milk and it's not hard yet. Somewhere in between is soft dough. Another way of looking at it is if you look at the stalk itself, you start getting the stalk turning a golden color. Some people cut into that bottom node and look and see if it looks like it's closed off, and if it's closed off, it's not going to be pulling water up through it. People have a lot of different ways of determining what soft dough is. But, something similar to this, I tend to stick a thumbnail into the kernel, and if that indentation that it makes disappears almost immediately after pressure is released and it's not real milky, then that's soft dough. I put this slide in because Larry Robertson with U of I retired at Aberdeen took pictures at each crop stage on both barley and wheat one year, and just visually looking at this, here's early milk, here's soft dough, here's hard dough. Can you drive by and from the pickup tell that it's soft dough or hard dough? Probably not. Visual appearance just on the surface of things just does not look like a real good indicator. And that's why I put that slide in. I think what the bottom take-home message is here is if you drive by in the pickup, well, you see a little difference in color there. But if you drive by in the pickup and you start seeing firing and changing color on the stems, you're definitely past hard dough. And so it's definitely time to shut the water off when you start seeing a change in color on the stems. Okay, just another way of summarizing what if for different soil textures and different root zone depths, the water that's held on a light textured soil, again, on a light textured silt loam soil, you have about 2 inches available that could be used by the plant if you had a 24-inch root zone. You've got 2.4 inches if you've got a heavier textured silt loam, 1.6, 1.7 on a sandy loam. So the bottom line down here is how much irrigation water do we need to apply after soft dough for each one of these textures and each one of these depths. If we have at soft dough the top 2 feet filled to field capacity. If that's the case and we've got a sandy loam soil, we're 1 foot deep, we're still going to have to add another 1.2 inches or so after soft dough to avoid some stress. A light textured silt loam will probably still need to add 1 inch, and we'll maybe need some even with a heavier textured silt loam. If we have a 2-foot working root zone, you see that the only time we need to add any water is a little bit on a sandy loam soil, depending on how much we're willing to gamble. And so there again, we come back to saying if the soil profile is at least 2 feet deep and it's filled to field capacity at soft dough, you have a silt loam textured soil, you probably are ready to shut the water off. If you've got a sandy loam soil, it's marginal. If you've got most years, you could probably still get by with that. Now, I show this slide because this was from our barley study. This is soil water content. And so it's bone dry here, here's wilting point right here, and here's field capacity over here, and then this is depth. And it's really not furlongs per fortnight, it's really soil depth in centimeters, which means about as much. 1 foot, 2 foot, 3 feet, and 4 feet. So you can see here we started off, when we shut the water off here, it was right here, and then at harvest, when we shut the water off at post-soft dough, about a hard dough, by harvest, we still had this much water in the top foot, this much in the second foot, this in the third, and no change down here in the fourth. When we shut it off at milk, on the other hand, notice that in the first foot, we're dried out to at least wilting point. We're down close to wilting point in the second foot, down close in the third foot. We've used some water out of that third foot. Nothing happens down in the fourth foot. And so you can see roughly where that plant can pull water from and how dry it can get water, and remembering that this was not that much different, maybe still about 85 to 90% of maximum yield, and it still almost made quality for malting. So plants can be pretty hardy. With that, I think I'll probably skip through this just very quickly and call it good. I did a little bit of an analysis that said, well, what's the relative value based on the relative yield at soft dough with soft dough as the base? What's the yield worth? At milk, we had 87% of the yield that we had at soft dough. So the relative price based on quality said, Here we had small kernels and marginal quality. Here we had black tip. Here was best for quality. And the relative crop value came out the best at milk. You notice that it was close at pre-soft dough. It was lowest at milk, low again at post-soft dough. And depending on the value, this was obviously not this last year, but we came out with a maximum value of production at soft dough. And so with that, questions or comments?